Log on, tune in, find out. Another good idea from Cambridge.
I think today is going to be sort of a hodgepodge of leftover topics. So here are some of the things I want to talk about. So I think I'll say a little bit more about purity and pointwise purity. Maybe something about the Springer correspondence. Something that I meant to talk about much earlier in the week, but didn't have time for, which is intersection cohomology, which is one of the motivations for the theory of perverse sheaves, and it's also the origin of the letters IC. And then maybe I'll finish with what happens in the setting of coherent sheaves. Okay, so for purity, so let me just remind you. I won't write down the full definitions again because, of course, those took forever. But so pointwise purity was a very strict condition on a single sheaf, well, we defined pointwise purity, and then we defined mixed, and then we defined purity as a condition on the derived category. So this is a condition on chain complexes of sheaves. And even though we had to define pointwise purity first, a pure sheaf doesn't have to have pointwise pure cohomology sheaves, because the purity here, I mean, there are two inequalities. There is less than inequality, and then the greater than inequality was defined in terms of the less than inequality by Verde duality. So this is not necessarily not necessarily sort of directly related to pointwise purity. Well, we had one exception. Well, actually, maybe before I go on, I should make a slightly more precise definition. So let's call an object in the derived category. So this is going to be in the mixed category, which we introduced yesterday. Let's call an object like that pointwise pure if all its cohomology sheaves are pointwise pure. And just like with the usual purity, there's going to be a shift based on the degree of the cohomology sheaf you're taking. So this should be pointwise pure of weight W plus K. So this is pointwise pure of weight W if the kth cohomology sheaf is pointwise pure of weight W plus K. So yesterday, one thing we learned was that for a local system on a smooth variety, pure and these two notions are equivalent. Pure is the same as pointwise pure. But in general, well, maybe I'm just saying more precisely what I mean by not related. In general, these don't have, neither one implies the other. But something remarkable happens for some of the perverse sheaves that are of the greatest interest in representation theory. And I guess this theorem is, well, probably due to Kazhdan Lustig, the flag variety. Well, let me state the theorem. So simple perverse sheaves on the flag variety and on the nilpotent variety are both pure and pointwise pure. So for the nilpotent variety, the reference I know for this is a paper of Lustig. And so what this says, so of course these varieties are certainly not, well, so the nilpotent variety is certainly not smooth. On the flag variety, we're talking about Schubert variety, so closures of B orbits. Those are also certainly not smooth. And the simple perverse sheaf, well, it's a local system over the open part of its support, but certainly the whole thing is not a local system. So this is quite a surprising statement, and it has strong consequences for what the stalks of simple perverse sheaves can be. And this result is a key step on the way to sort of computing what these things actually are. So this is a, well, yeah, so this has major consequences for computing the IC objects. So I've talked at various times this week about computing these IC objects and writing them down as polynomials and stuff. Once you have a guess as to what those polynomials are, proving that you've got the right thing, that you haven't mixed up pieces of different perverse sheaves or something like this, often depends on this kind of statement. And this is something that sort of, I feel like I don't have a lot of intuition for this. There's something special about these varieties that makes this very strong thing be true. And it doesn't seem to be something general in nature. So anyway, so that's one thing. Okay. So then topic 2 is the Springer correspondence. So this also has to do with the nilpotent variety. I've mentioned this earlier in the week, so now I'll say a little bit more precisely what this is. And then n tilde, so this is going to be a nilpotent variety in Lie algebra G of a, let's say, a complex reductive algebraic group G. And then n tilde is going to be the set of pairs x comma b. So x is a nilpotent element, and b is a Borel subalgebra containing x. Okay. And then so then, of course, you can forget the Borel, and then that's a map from n tilde to n. And here are some facts. N tilde is smooth. This is pretty easy. I mean, it's maybe not completely obvious from this description, but you can also think of this as the cotangent bundle to the flag variety. So then it's sort of obviously smooth. And pi is semi-small and proper. So then we can invoke the decomposition theorem from yesterday. And then we find out that the derived push forward of the constant sheaf shifted by the dimension is semi-simple. So it's supposed to be a direct sum of simple perverse sheaves. So the kinds of things that occur here are ICSL. So S is a nilpotent orbit, and L is an irreducible local system on S. So I've written this as a sum over all nilpotent orbits and all local systems, and each one of these, each particular one, well, so right now the sum runs over all possible simple perverse sheaves here. Each one may occur with some multiplicity. Some of them may not occur. So I'm going to record the multiplicity by just formally tensoring with the vector space. So this is a complex vector space, and then so what I'm doing is recording the multiplicity here. So in other words, the dimension of VSL is the multiplicity of ICSL in this big perverse sheaf that we've constructed. So R pi star C dim n. Okay. So far, all we've done is invoke the decomposition theorem, and then the result, which is well, the original version of this was due to Springer, but the version I'm describing was due to Borholm and McPherson. And the result says the following things. One is that each non-zero vector space over there, so some of those may be 0, but the ones that are not 0 carry irreducible representations of the Weil group. And then the second part is that, in fact, every irreducible representation of the Weil group occurs as exactly one of those. So every irreducible Weil group representation occurs exactly once in the big direct sum. Okay, so that means that in particular, you can take a Weil group representation, look for it in this direct sum, and then find out that it's labeled by some particular nilpotent orbit and some particular local system. So you get a map from the irreducible representations of the Weil group to pairs consisting of a nilpotent orbit and a local system. And this is what this map is what's called the Springer correspondence. Okay. Okay. All right. Okay. So maybe I'll go into the next thing. So intersection chromology. This topic is maybe sort of more algebraic topological in nature rather than representation theoretic. So let me remind you of something we did on Monday. Right at the end of my lecture on Monday, I talked about how to get classical Poincaré duality out of Verde duality on the derived category. So the setup was the following picture. What we were going to do is take so this is for X, a compact orientable manifold. And then what I want to do is take the Verdet dual of the constant sheaf, and then take derived global sections, and then take cohomology of that, and then evaluate that in two different ways. And one way was to compute that the dual of the constant sheaf is just the constant sheaf with a shift. And the other way was to compute that the functors R gamma and Verdet dual commute. And then when you do the thing on the left, you just get the ordinary cohomology, but with a shift because there's a shift in that sheaf. So you get Hn plus the dimension of X. You get the n plus dim X cohomology group of X. And on this side, you get the negative n cohomology group of X with a vector space dual. So this was classical Poincare duality. Now, what I want to do is sort of develop an analog of this that works on non-smooth things. And then instead of using the constant sheaf at the top of that triangle, I'm going to use a simple perverse sheaf. And the reason that this is a good idea is that, well, the perverse T structure was defined like this. I won't write out the full definition, but there's some definition for the less than or equal to 0 part. And then the greater than or equal to 0 part was just defined to be the Verdet dual of the less than or equal to 0 part. So just from those formulas, it's clear that the heart of the T structure, so the abelian category of perverse sheaves, which is the intersection of the less than or equal to 0 part with the greater than or equal to 0 part, is well, it's stable under the duality functor. So the duality functor, well, it's an equivalent. Well, it's an anti-equivalence of categories of the whole derived category with itself. But since this is stable under it, that means that D induces an anti-auto equivalence of the category of perverse sheaves. So now we have an abelian category with some non-trivial self-equivalence. And so in particular, well, because you can pick out simple objects in an abelian category by sort of abstract categorical definitions. This is something that's come up in some other talks, and of course in the category of perverse sheaves, that's the only way to pick out what the simple objects are. So D must take simple objects to simple objects. So in particular, well, so that means that the Verdet dual of a simple perverse sheaf, which means some ICSL, has to be another IC. Okay, so, well, which IC is it? Verdet duality is defined by taking Arham into some particular sheaf, and that operation doesn't change the support of whatever you started with. So whatever support you start with, well, this object is supported on the closure of S, and the answer has to be supported on the closure of S also. So what's there has to be an S. And then there's some local system here. Well, you could just denote that L check But in fact, L check is what that kind of orientation really ought to denote. It's the dual local system to L. Okay. So here's a special case of this. If you take the dual of an IC with the trivial local system, well, the trivial local system is its own dual, so that means that you found a self-dual object in the derived category of constructible sheaves. Okay, so now let's assume that S is a dense open stratum in X. So this is certainly something that you have in lots of examples, like the nilpotent cone or whatever certainly has a dense open orbit. So if you have a dense open stratum, then the support of ICS with a trivial local system is the whole space. Okay. Let me introduce an object which I'll call IC tilde, and this is going to be the same object but with a shift, and the shift is going to be minus 1/2 the dimension of S. Okay, so this is back to real dimension, by the way. Okay, and now what I want to do is just copy that triangle on that board with a constant sheaf replaced by IC tilde. So what I'm going to do is take derived global sections of IC tilde, and then take the nth cohomology of that. And then I could compute that in two ways. One way is I could compute the Verdet dual of IC tilde. And, well, actually, that Verdet dual is already computed. I just have to figure out what happens to this shift when you plug it into that formula, which says the unshifted object is exactly self-dual. And then it turns out that the dual of IC tilde, well, the dual of IC tilde has a shift in it, and the shift is the dimension of X. Okay, so that's exactly what we had over here. So the cohomology group you get down here is the n plus dim X cohomology group of X. So it's sheaf cohomology, or maybe it should be called sheaf hypercohomology or something, with coefficients in the complex of sheaves called IC tilde. And then if we go the other way, well, let's still assume that X is compact. There's a non-compact version of this, which is only slightly more complicated, but maybe I'll stick to this for now. This fact is still valid in complete generality, and then you get exactly the same thing down here. You get that H minus n of X with coefficients in IC tilde. With a vector space dual on the end. So this is so this isomorphism down here. This was discovered by Goreski and McPherson in the late 1970s, sorry, where? Oh, here. Oh, right here. Yes, thanks. Okay, yeah. So this is this isomorphism along the bottom was discovered by Goreski and McPherson, and this is something like Poincaré duality for singular spaces. So the one assumption that's not here is that X need not be a manifold, the groups the groups that are on the bottom of that diagram right there are called the intersection cohomology groups of X. So HK of X IC tilde. Well, the other notation for this is IHK of X, and those are called the intersection cohomology groups. These were defined originally by Gretzky and McPherson by a different method that didn't involve derived categories or Verde duality or sheaf theory or anything. They defined it in a very concrete way by taking the usual construction of singular cohomology groups for a topological space and modifying it to sort of change what happens along smaller strata in a stratification. And then they discovered that they could do this modification in such a way that they recover Poincare duality for spaces that you wouldn't expect to have it. And then I think it was an observation of Deligne that the groups that they had defined were actually the sheaf cohomology for a particular complex of sheaves. So essentially, what happened was that before the theory of perverse sheaves was really fully developed, the first step in the development was the discovery of a particular single perverse sheaf, and then the later theories developed by Bailenson, Bernstein, and Deligne, putting it in the context of this abelian category obtained by T structure on this derived category. So the parameter S. Okay. So here I said that S should be an open dense stratum. So basically, so if you start with just a topological space, then you want it to contain some open dense set which is a manifold, but it's allowed to contain smaller strata which are not manifolds. Part of what is done in one of the papers of Gretzky and McPherson is prove that these groups are independent of the stratification that you use for the smaller strata. So that's why S doesn't appear in this notation. All right. So maybe I'll spend the rest of the time on the coherent world. So the analog of perverse sheaves in the coherent world, I guess, was developed sometime in the 1980s by Deligne in some handwritten notes, and then later written up by Bezrukovnikov. What's that? Bezruk. Okay, thanks. Okay. Okay, so I'm gonna impose some extra conditions here, which are not really necessary for the theory. So I'm gonna say that X is a variety over an algebraically closed field. A good chunk of the theory works in really extreme generality, where you take X to be a scheme over some Noetherian base scheme that admits some kind of duality functor. But anyway, so some things don't work in that generality. So I think I'll just stick to this from the beginning. And for now, let's fix a stratification. Okay, so just like usual, and then so co X is going to be the abelian category of coherent sheaves on X. And then my habit is to write cursive letters in place of Roman letters for things in the coherent world. So script dbx is going to mean the bounded derived category of the abelian category of coherent sheaves. Okay, so that's what that means. And then here are the first two observations that sort of suggest that this might be something worth trying. So in the classical constructible world that we've been working in for the past 4 days, this idea of Poincare-Verdier duality, of course, has been everywhere. Sometimes only in the background, but it's sort of always been there. And there's a coherent version of that. The original version of this was discovered by Serre in the 1950s, but the derived category version of this was developed by Grothendieck and his school, I guess, in the 1960s. So there's some duality functor, and well, I guess I can't think of a different letter to use for Serre-Grothendieck duality, so I'll just put subscripts on it like that. And then, well, the sort of basic kind of sheaf that we've been talking about in the constructible world is local systems. So constructible sheaves are built out of local systems on strata, and a local system, well, let me say what a local system is in a slightly different way. A constant sheaf just means a direct sum of copies of the trivial local system, so a free sheaf over the constant sheaf. And then a local system is one that's locally free over the constant sheaf Cx. So in the coherent world, well, what you're talking about is modules, or maybe I should add this notation. So Ox is going to be the structure sheaf. So coherent sheaf, of course, is a module over Ox. So the analog of a local system is going to be a locally free sheaf over Ox instead of Cx. And another name for that is vector bundle. Okay. So vector bundles are supposed to play the role in the coherent theory that local systems play in the constructible theory. And then the goal, well, find a T structure. Well, we have this duality functor. And one of the key properties of the perverse T structure in the constructible case is that it's self-dual. That's what just came up in this intersection chromology business. So we want to find a self-dual T structure on the coherent derived category. Well, not exactly on the coherent derived category, rather on the subcategory of objects that are, well, I don't want to reuse the word constructible because constructible has a fixed meaning, but what I want to do is write down the coherent analog of constructible. So that's going to mean that we want to take objects that when you restrict them to a stratum, they give you vector bundles. So they're vector bundles along strata. OK, so this is going to be some kind of definition of a category. Complexes whose cohomology have this property. So, so yeah. Yeah. I'll get to that. So there are a bunch of problems with trying to do this. So the first problem is that, both kinds of duality, Verdier duality and Grothendieck duality, involve some kind of dimension shift. I mean, that's something that we recognize from sort of classical Poincaré duality. But the kind of dimension that comes up is different. I mean, Verdier duality is really sort of, at heart, a topological thing. And then the dimension that comes up is real dimension. In Serre-Grothendieck duality, what comes up is complex dimension. So this involves, or I guess algebraic dimension. So this involves algebraic dimension and not real dimension. And the consequence of that is that if you have any chance of finding something that's self-dual, well, we had all these factors of a half that have shown up in various formulas. And that was OK because we assumed even real dimension. So now we need a stronger condition. We need even algebraic, we need the strata to have even algebraic dimension. This is, I mean, of course, if you require strata of a complex variety to have even real dimension, that's not a condition. They automatically do. But requiring them to have even complex dimension is a strong restriction. OK, so that's one problem. That's not so serious. It just means that we're going to have to throw out a lot of varieties. I mean, only some varieties will be sort of reasonable to work on. The second problem is that, restriction of coherent sheaves to a stratum is not an exact functor. This is different from the constructible case. If you have a sheaf of vector spaces and you restrict it, then you have a sheaf of vector spaces, and that's fine. If you take a coherent sheaf and you restrict it, well, the result is not a coherent sheaf over the smaller variety that you're on now. You have to tensor with the structure sheaf of the new variety, and tensoring is not exact. So this means that that you have to replace restriction. Well, you have to be careful. You either have to do derived restriction, or, well, you just have to be careful about the order in which you do restriction and taking of cohomology, because they don't commute anymore. So restriction and cohomology don't commute. So this is again not necessarily a fatal problem. It just means that, well, throughout the rest of this week I've been sloppy about taking cohomology and restrictions, and you can't be sloppy anymore. But the third problem really is kind of fatal. And the third problem is that this sentence over here, star, which was supposed to be the definition of a full subcategory of dbx, the problem is it's not a full triangulated subcategory. I mean, it's not triangulated. In other words, you can take two objects that satisfy this condition and a map between them, and the cone won't have this condition anymore. In fact, you can see this. It's not something special about the derived category. It's something about vector bundles. You can take a map of vector bundles and very easily construct examples where the co-kernel just isn't a vector bundle. So that's a really bad problem. But there's an extra condition we can impose to fix it. And here's the condition we're going to impose. We're going to assume that an algebraic group G acts on X with finitely many orbits. And we're going to take the orbits to be the strata, so stratify by orbits. And then work in the category I'm going to denote dgx. So this is the bounded derived category of the category of G-equivariant coherent sheaves. The reason that this makes a difference is that a G-equivariant coherent sheaf on one orbit, well, it has to be locally free. So the G structure, I mean, the problem with this definition of star is that you just can't force arbitrary coherent sheaves to obey your chosen stratification. I mean, you can't do it by willpower, but you can do it by imposing a G action. So a G-equivalent coherent sheaf is automatically locally free on one orbit. Okay, so then that definition star makes sense. Okay. Okay. So then you can, in fact, write down a definition which looks a lot like the definition of perverse sheaves we wrote down on Tuesday. You get a T structure, and then it has a lot of properties that look quite familiar to us. So let me call this theorem 1. So the parts of this are, so let script P of x be the heart of this T structure, which is the category of perverse coherent sheaves. So the first property is that every object has finite length. The second property is that, well, there's a nice list of simple objects that looks a lot like the classification of simple objects for classical perverse sheaves. So the simple objects are, well, I'll denote them with a script IC. So we're going to label them by specifying a stratum. And, well, the second thing is not going to be a local system anymore. It's going to be an irreducible vector bundle. So this is an irreducible G-equivariant vector bundle on S. And then the third thing is a duality property that looks just like the Poincaré-Verde duality property we had a little while ago when we were talking about intersection cohomology. The Serre-Grothendieck duality induces an anti-auto equivalence of the category of perverse coherent sheaves. And then the dual of a simple object better be another simple object. And then, so in fact, it's the simple object with the same support and the dual vector bundle plugged in. So, okay. Sorry? I'm sorry, what was the question? Where do I mean G-equivariant? Everything is G-equivariant. So yeah, so everything is G-equivariant. So this assumption of a G action is in force throughout. So yeah, so Px is the heart of a T structure inside dgx. Yeah, so on something like an ind scheme, so you can certainly deal with a finite dimensional piece of it at a time. So finite dimensional pieces of that have finitely many orbits. I mean, I don't have a, I mean, and then maybe you can sort of form some sort of increasing union of categories. I don't have a good sense of what it means to talk about coherent sheaves on an ind scheme. So I mean, I'm sure some sort of technical issues come up there, and I don't exactly know sort of what kinds of care has to be taken to deal with that. Yeah, so the main example of this that's found use is not on an ind scheme. It's on the nilpotent cone, and of course the group acts on the nilpotent cone with finitely many orbits, and then Bezrukovnikov has used perverse coherent sheaves on N to prove a conjecture of Lustig and Vogel on well, it's a conjecture on bases for the G equivariant K theory of the nilpotent cone. All right. So maybe in the last couple of minutes, I'll say a tiny bit about a new construction of a category called the category of staggered sheaves. So this was introduced in a paper by me, and then a lot of the main theorems are worked out jointly with David Truman. And the basic idea is to use some extra information from the G action to impose some kind of filtration on the construction of perverse coherent sheaves. This is sort of morally what's going on. It's not literally a filtration on that construction. It's something slightly different. It's a filtered looking modification, maybe. On the perverse coherent sheaf construction. And then and then so when you do this, you get a new T structure on the derived equivariant coherent category. In general, it's different from that, and let me call its heart script M of X. So the objects of the heart are called staggered sheaves. So I'll say a little bit about properties of staggered sheaves. Well, I guess the first three properties of staggered sheaves are the same as for perverse coherent sheaves. So maybe I'll just erase the first line of this, and then so now this is for staggered sheaves. But then there are a number of additional properties which seem to be better than what happens with perverse coherent sheaves. the first thing that happens with staggered sheaves is that we can get rid of the even dimension restriction on orbits. So this is not exactly, I mean, I guess this doesn't really belong as a point of a theorem. It's just that it's not a necessary assumption. So orbits need not have even dimension. And so this opens up a lot more varieties, like the flag variety, various kinds of, you know, the variety you get from a real nilpotent cone through the constant Sekiguchi correspondence. Those are examples of varieties that come up in representation theory where the orbits don't have even dimension. The next property is that with this sort of filtered construction, you get some analog of a weight structure on the derived category. With respect to this weight structure, there are analogs of the theorems we talked about for classical perverse sheaves yesterday. So one is that every simple staggered sheaf is pure. And second is that every pure object is semi-simple. And actually, I mean, the work in proving this part of the theorem is all in setting up this structure. Once you have the appropriate structure on the derived category and you have some appropriate Ham theorems, deducing these two statements from those results is really identical to the proofs I did on the board yesterday for perverse sheaves. And then the last two properties. The last two properties are properties that resemble the kind of things that happen in things like category O or highest weight categories in the sense of Klein, Partial, and Scott. So one is that this category, the abelian category, has enough projectives and injectives. And then the last one is that it has a collection of standard modules, standard objects. So these are analogs of Verma modules. So there are some indecomposable objects with some canonical characterization such that, well, the set of isomorphism classes of them is in bijection with the class of simple objects, and each simple is a quotient of a unique one of these. And it has the dual version also. It has co-standard objects. So each simple is a sub-object of a unique co-standard object. OK, so maybe I'll just stop there.